Oh, good afternoon. I will just have challenges facing satellite laser ranging systems. Many thanks for the previous presenters. I will just follow on and just making some additional comments or points out. For satellite laser ranging, the SLR system is, as we will see and as you definitely know, is not serving for SLR only or most of them, but anyway, it is the most important one. And obviously, precision, accuracy, and stability. Stability, I would like to point out, is one of the key points, again, mentioned many times before, as a key performance. Also, the productivity, because of the number of targets is increasing, including lunar laser ranging. And there is a new part of work appearing, and hopefully several missions are on the high degree of preparation. Hopefully they will appear, and this is another challenge for SLR sites. There will be a special talk by Jan, so I will just partially mention it. And the same with space debris laser ranging and optical tracking. Again, will be a special talk. I will just mention a few points for that. But as a follow-on, as a result, mostly of space debris laser ranging is appearing of new wavelengths. I will spend some words on new wavelengths as a new challenge for SLR sites. Okay, SLR precision. In fact, most of the stations now are showing reasonably good precision on the order of from few millimeters single shot to several centimeters single shot, and normal point precision nowadays is on the millimeter or even sub-millimeter level. However, system delay stability is a permanent issue. We have heard in the two previous talks. Again, I will spend some time more to discuss it. Again, 1 millimeter system stability is a GGOS goal, and it is a crucial parameter even for, or especially for laser time transfer, because in SLR, everybody knows, you are compensating a lot of delay changes by calibration of your ground target, internal or external anyway. You are compensating for some changes of delays. However, for laser time transfer, you are definitely not compensating those. Especially for laser time transfer, this is the very critical issue, and it is not removed by ground target calibration, or not removed fully. Another big challenge is station productivity, which is becoming more and more important. The number of SLR targets we have heard, I think, yesterday from 122 days will jump up to 140 in the very near future, I don't know, 1 or 2 years. And so SLR tracking, scheduling, and planning, and so on, is a very delicate issue, and it is really a challenge to adjust the well tracking. And there are many different interests and priorities. You have heard sometimes it is good to jump from one path to another one, to interleave them, and so on. Sometimes it makes sense to keep tracking to very low elevation, and so on. So it is quite delicate. It's becoming more and more delicate, even this item. Special issue, I will not spend too much time, is the lunar laser ranging. Number of targets is increasing slowly but still, and new targets are appearing, and new technologies as near infrared is opening a little bit the door even for stations with smaller telescope and not with ideal locations like Wetzell to make a nice lunar laser ranging in ideal conditions. Everybody knows this kind of graph. This is the station system delay. This is Graz station. I think this is the most stable you can find. What I would like to point out It's absolutely perfectly behaving from middle of 2012 up to 2014, or even a bit more. It is plus minus within 1 millimeter over these 2 years. Time deviation is an important parameter, especially for laser time transfer. So all the stabilities and delays are stable in time deviation, meaning better than 1 picosecond over a week. It's a dream value. Why I'm showing it? Why? What happened? That the jump is understandable. Somebody touched some connector or exchanged a piece of cable. But why? It is not as stable as before. It was nicely 2 years before. I think, anyway, these are the best values of any other SLR stations. Remember, this is 50 picoseconds per division. If you are look on the other stations, they are by orders higher scale in the vertical. So these are still quite good results. But what I would like to point the station, what I would like to address, the station operators should keep in mind and study and think about what is happening, what we have changed, why we are not as good as we were before. Even the jump may be understood, and it is compensated by the calibration procedure, but this one is very suspicious, and even for SLR results, it is a very good chance to make some systematic non-stability. So that's why I'm spending so much time on this single graph. Key requirement, system stability. For the laser time transfer, again, it will be a special talk. The special requirement on the station, aside of the system stability, is a laser fire control shot by shot. The minimum rate is 100 hertz, the standard rate is 1 kilohertz, and every shot should be fired in the predefined epoch with the better than 100 nanosecond because of the strategy of measurement and because of the principle of laser time transfer. On single photon level, it was not valid for T2L2, but for all the future, it seems, single photon missions, it will be this requirement. Obviously, you have to have connected the SLR system to high quality clocks, and more detail in the next talk. Space debris. The key point is an error budget, obviously. You don't need high energy laser, nothing new. Maximum photon detection efficiency detector. And this brings the question of new wavelengths. I will use the next slide for the new wavelengths. And I will have a special presentation on Thursday morning or before the lunch about our new 1 micron detector for SLR. An optional capability of CW signal, optical signal monitoring, and images recording with calibration coordinate data. And again, will be a special presentation from Graz in this session. New wavelengths. Obviously, there is strong interest in the near infrared. 106, because it is natural fundamental wavelength of mostly used neodymium YAG laser. And 1.5, or even nowadays, ESA is doing some studies to use for ground-to-space communication and even ranging for 2 micron, 2.2 micrometers. So it is completely new area. 106 has a special advantages versus green. It is known, it is never-ending story since NDR last 20 years. Just to remember, not generating second harmonic, you will gain about a factor of 2 because the photon energy is 1/2, so we are gaining factor of another 2. Atmospheric attenuation, 2-way, it's between 1.2, 1.5, or even higher. So if you will multiply this thing, you are at the factor of, you are on the factor of 6 or even more. And going to the lunar laser ranging, there is this high probability that the dust, just like on the lunar hot and all these echoes, is better avoided or lower attenuation by 1 micron. So together, this one is strong argument in favor of 1 micron. It was pioneered by Clément and Johann Eckel in Wetzel already a few years ago. And I will show the package after tomorrow in the dedicated technology session. Okay, conclusion. Although SLR became a routine procedure within the last decade, we are still facing new and new challenges. Just to give you an idea, I did start SLR business 47 years ago, 1975. And at that time was a challenge to get 5 echoes per pass. Having 5 echoes and more, there was a celebration. We have 1 pass overnight, and this was a challenge. And nowadays, nobody is taking care. So there are still challenges, but a bit different scale. And that's all. Thanks.
Thank you. Thank you, Ivan.